Okay, so hello everyone. Let's continue our topic on the fundamentals of environmental engineering and science. So this class we're going to talk about the material and energy balances. So before we introduce the contents, let's still do a recap of our last class. In last class, we talked about what is molarity. So molarity means the concentration of certain species in liquid or in water, right? It is shown with a unit of m, and it is directly related with how many moles of these solutes are there in the water system. For example, if we have 1 mole of sodium chloride per 1 liter of the solution, then we know that the molarity for sodium chloride is 1m. We also talk about the the normality. Normality is related with the exchange or transport of the electrons or the protons when we talk about the oxidation reduction reactions or the acid-base neutralization reactions. And also we want to understand what is the difference between them. For the normality, if there are exchanges or transport of the protons or electrons that are more than 1, then we have to multiply that extra number into the molarity to obtain the normality. Also, we showed how we can calculate the equivalent weight, because if equivalent weight also considers the transport of how many electrons or protons that's occurring in these reactions. We also talk about how we can calculate the concentration in milli equivalent per liter. We talked about what is buffer, and specifically we talk about the bicarbonate as a buffer. So finally, we deal with the alkalinity. So how can we use milligram per liter as carbon dioxide to calculate the alkalinity? How can we determine the alkalinity? So alkalinity means how resistant the solution is in regards to the acid, right? So how we can calculate the concentrations of different carbonate species in water if the pH is known. So we can use the KSP, or the solubility product, to calculate the concentrations of different ionic species. Finally, in an open system, which carbon species is a constant. So this is determined by the Henry's constant, right? So we can calculate the concentration of the carbonic acid. All right, so in this class, we're going to continue on the topic of the materials and energy balance. So the course objectives are, first, to solve the mass balance problems in different systems. And secondly, we want to show several reactors and also try to understand how the concentration or how material is being conserved within different types of the reactors. So first, let's give an example. So just consider you just did a grocery and try to you purchased some vegetables and bring it back home. Okay, so now let's build a mass balance of these vegetables in your home. Okay, so vegetables are bringing into your home as the consumer goods, and some of the vegetables are being consumed. For example, you cook for dinner, cook for lunch, breakfast, right? Eat all of them, right? And also, if you, for example, if you have some pets, you wish to share some vegetable with them, maybe they can also eat that. And of course, the bacteria will consume these vegetables as time goes on, right? And not only that, in your home, if you cannot finish all of these vegetables, they can also get accumulated. And also, some of the vegetables will go through digestion, and then you might also toss some of these vegetables, and that will go to the solid waste. And now, if we build a control volume, so if we choose an imaginary boundary and just use your home as a control volume, we can build up an equation, right? Because we have the inflow, we have the outflow, and also we know what is going on inside the home, right? So this is going to give us a general concept regarding the mass balance. Especially for this problem, for this case, we know that the purchased food, which is the inflow, is going to be equal to the family consumption. And this consumption involves all the types of the consumptions, plus the waste, which is basically the outflow, and the stock, which is accumulation. So we can also rearrange this equation here and put the accumulation on the left-hand side. And you can see that accumulation is equal to input minus output minus the consumption. Okay, so we talk about the definition of the control volume. So control volume is a boundary that is selected for your calculation. For this case, you choose your house as the control volume just for convenience, correct? And we can use a more engineering or scientific way to represent this relationship here. So if we think back on this relationship, you can see that accumulation can be represented as a function of input, output, and consumption, right? And because of that, we can say that the rate of accumulation, now let's talk about the accumulation in terms of time. So the rate of accumulation is going to be the rate of the input minus the rate of the output and minus the rate of the consumption. So if we write this equation out in mathematics, you can see that here the total, the capitalized M means the mass of the food in your home. So dm dt is going to be equal to the rate of the input, din dt, minus the rate of the output, which is solid waste going out of your house, d out dt, minus r here. Okay, so if we further look at the input is going to be the concentration multiplied by the flow rate. Okay, and the rate of the output is going to be the concentration multiplied by the outflow or the exit flow rate. And the rate of consumption, we can still use the R here. Okay, so this is a more mathematical way to represent this mass balance here. Or we can also build a relationship that by just doing a few rearrangement, you can see that the rate of input is going to be equal to the rate of output plus rate of the consumption and plus the rate of the accumulation. So this is going to be the same as this equation here. Okay. Okay. So we can use this mass balance to look at all different systems and try to solve for the mass balance equations. Okay. So for example, in a system that doesn't have any chemical or biological reactions, which means that there is no consumption here. Okay, so how this equation is going to get changed. So actually this system can be used in a lot of physical processes. So what this means is that the total mass into the system is equal to the total mass out of the system plus accumulation. And we actually use this system quite a lot. So think back on the filtration system that we discussed in our first class. So basically the filtration will remove some particles or some suspended solids that are existing in the water, right? The accumulation is going to be a negative term here. So then that's going to be related with the total suspended particle into the flow and related with the total particle amount out of the flow. So actually this is so filtration is one type of the physical treatment. And for physical treatment of the water, we define this efficiency term, eta here, which is equal to the mass in, which are the total suspended particles or pollutants into the flow, minus the mass out divided by the mass in. So basically, if we further consider that the flow rate in and out are the same, then we can represent this equation with these three different concentrations, which are C in minus C out divided by C in. So here we have a brief example here. Let's say we have a primary clarifier, suspended particle removal, or suspended solid removal. Okay, so we know that the total flow rate is 2 meters cubed per second, and you can realize later that this is not affecting the results. Okay, so the inflow of the suspended solids are 200 milligram per liter, and the effluent are 80 milligram per liter. Since there's no reaction taking place, then the accumulation or the removal of the particles or removal of the suspended solids is going to be 120 milligram per liter. So for this system, if you want to calculate the physical treatment efficiency, then we can just plug in this equation here. And then that's going to be 200 minus 80 divided by 80. You can see that the removal the efficiency is 60%. So there are also systems that there's neither accumulation or reactions, and this system applies for many of the water transportation systems. So if you think of the flow of different streams, right? Let's say you have two streams combining into one stream. Okay, so let's say there are some suspended solids again in the stream, and then if they mix together, then at any location there's no accumulation or reaction taking place. And this is going to give us basically the complete mass conservation, right? So whatever goes in should be equal to whatever comes out. Okay, so here's another simple example here. Let's say we have a storm sewer, and this sewer carries snowmelt with a concentration or salt concentration of 1.2 gram per liter. So typically the salt concentration within these sewer systems are going to be higher compared to the streams, because if you consider what a sewer being used, storm sewer being used, is basically it collects the groundwater in residential areas or industrial areas. Those are, for example, in the parking garage, you have a higher concentration of the salt, and then they're going to get collected by these storm sewers. And then they can further mix with the stream, right? The stream is going to have a lower concentration of the salt. So further, we know that the flow rate of the snowmelt is 2,000 liters per minute, and the stream is at a flow rate of 2 cubic meter per second. And wants us to calculate what is the final salt concentration after the mixing of this storm sewer or this snowmelt with the stream. So how can we solve this problem with mass balance? So similarly, if we can draw a schematic diagram of this system, we know that it's composed of a mainstream, right? The mainstream is at a flow rate of 2 meter cube per second. Okay, it also has a concentration of 20 milligram per liter. And for this snowmelt, it's at a flow rate of 2,000 liter per minute. And then it's at a concentration of 1.2 gram per liter. Okay, so we have to pay attention to these units here, because there are quite drastic differences in these numbers. But you can then realize that the flow rate of the snowmelt is really incomparable to this flow rate in the stream, because here we're representing the flow rate in liters and in minutes, right? So if you further convert that into meter cube per second, you can find that 2,000 liters is equal to 2 meter cubed, right? Cubic meter. And then that's per minute. So we should further divide this 2,000 by 60 to convert that into cubic meter per second. Okay. So similarly, we should convert this unit here to 1,200 milligram per liter. Okay, so now we need to build up a mass balance. So one thing we know for sure is that the total flow rate after the mixing is going to be equal to the flow rate of these two streams, right? One is coming from the snowmelt, the other is coming from the mainstream. So we know that the total stream flow rate is going to be equal to 2 plus 2,000 divided by 1,000 divided by 60. Okay, so that's going to be equal to 2 plus 2 over 60. Okay, so the other mass balance is going to be related with the salt. Okay, so we know that the total mass of the salt that's coming from the snowmelt and the total mass of the salt that's coming from the stream is going to be equal to the total mass of the salt after the complete mixing. So we know that we can build up the relationship of C in multiplied by Q in plus or C1 multiplied by Q1 plus C2 multiplied by Q2 is going to be equal to C mix multiplied by Q total. Okay? So then we can start to plug in these numbers. So here it's showing a more clear schematic diagram here, right? So that's for the stream, it has a flow rate of 2 meter cube per second, right? And it has a concentration of 20 milligram per liter. And then we're also showing this snowmelt here. And then if we choose the control volume to be the mixing here, and then we can take a look at the total flow rate after mixing is going to be the flow rate, the combined flow rate of these two streams, right? And then we can, based on the mass in equal to mass out, then we can have this equation here. So further we can calculate that the C out or the C mix is going to be 39.3 milligram per liter. Okay? So since we have already learned these basic mass conservations, okay, so you can see that there is no reaction taking place. And now we have to include the reaction or the consumption of these different species within this control volume. And this is where we're going to introduce the reactors. So there are multiple reactors we're going to learn about. But here, let's first assume that all of the reactions follow the first order reaction. In our last class, we actually mentioned that the first order reaction is the most commonly seen reactions, right? Because a lot of reactions, the reaction rate really depends on the concentration of the species. So initially, if the concentration of species is really high, for example, A converting into B, if initially the concentration of A is really high, then there is going to be a higher reaction rate of this reaction, right? And as the concentration further goes down, then the reaction rate is going to get lower. So the first reactor we're going to introduce is the batch reactor. So the batch reactor is basically, you can understand that based on this name, we're conducting these reactions in batches. You can imagine this process as the cooking process. So at home, you have a pot, right? You're trying to cook some dishes. So you cannot let all the ingredients or let all the soup to flow from, or you don't have an inlet or an outlet for this pot here. So what happens is that you have to wait until the reaction is conducted. Then you can finish this reaction and then prepare or process the new materials. So basically what happens in the reactor is that you feed in all the ingredients and then you mix and let them react and then finally discharge, right? So because of that, for this reactions here, or for this to build this mass balance here, we know that there's no input or output here, okay? So the rate of the consumption is just equal to the rate of the accumulation, okay? So if we further build this relationship out, coming from the initial equations, you can see that the dc divided by dt is going to be negative r, where r is the reaction rate, okay? dc dt is the accumulation rate. And further, if we plug in the first order reaction, right, this is going to be negative kc. And then in our last class, we introduced that for the first order reactions, they're going to follow in an exponential decrease of the concentration, which means that C is going to be equal to C0 exponential minus KT. Okay, so as you can see, the longer the time goes, the lower the concentration. All right, this is a batch reactor. But for a lot of the engineering processes, we don't want batch reactions. For example, if we want to clarify the water from a stream, normally we don't want to collect all of these water and then put them into a tank or a container, let them react, discharge, and then feed in, right? Because we want the water to be continuously being processed. So this is where the other two types of the reactors come into the place. So the first commonly used the reactor type is called a plug flow reactor. So the plug flow reactor is just like a plug, right? So basically you have a space. You can think of that. Either it can be a cylinder or a square duct, so on and so forth, right? But there's a flow going through, okay? So while the flow is transporting, you can imagine these tiny slices, and these slices just move as due to the general velocity, due to the velocity of the flow in here. And what happens is that in each of these slides here, the reaction will take place. Okay, so now let's try to build up a relationship describing what is happening within this slice. Let's assume that here on the left hand side of the slice, the location is x, and on the right hand side of the slice, the location is x plus x. And let's also assume that the concentration on the right hand side is Cx plus delta x, and on the left hand side is called Cx. Okay, so further we know that the reaction rate is equal to negative Kc, or the reaction rate is equal to Kc. Okay, now let's try to build up a relationship that can describe this system. We know for a plug flow reactor, there's no net accumulation in any of the slices because there's just continuous movement, right? So in any control volume, there's no net accumulation, but there is consumption because of the reactions. And if we think back on the mass balance, we know that the inflow is going to be equal to the outflow plus the consumption. And further, if we represent these parameters out, we can see that the inflow is calculated by Cx multiplied by Q, right? And the outflow is equal to Cx plus delta x multiplied by Q. And then the consumption is going to be the reaction rate multiplied by the control volume. And here the control volume is this one single slice here, which is equal to R multiplied by V. And then we can further write this out as Kc multiplied by delta x multiplied by S. So the S here is basically the cross section of this plug flow reactor. Okay, so further we have the relationship that the Q is actually equal to S multiplied by the velocity, or the velocity of the liquid. Okay, and further delta x is equal to velocity of the liquid multiplied by delta t. So we can try to make some further arrangements here. So you can see that since Q is equal to S multiplied by V liquid, S multiplied by V liquid, okay? So we can cancel these cross-section areas here. And further, we can divide VL on both sides, and this is going to give us a delta T. So now let's further rearrange this equation. You can see that we can have the relationship of Cx plus delta x minus Cx divided by delta T equal to minus Kc. Okay, so on the left hand side, if the delta T goes to 0, then we have exactly dc dt equal to minus Kc, right? So this is basically how we can try to build up an equation that's describing this PFR plug flow reactor system. And you can see that the relationship, or this equation is very similar to a batch reactor. So basically, the equation that's describing the batch reactor and the PFR are the same, right? So if we further solve this differential equation, we know that C is equal to C0 exponential minus KT. Okay, so the concentration is going to decrease exponentially. And this is the feature of the plug flow reactor. And commonly, we also use another type of reactor called the completely mixing flow reactor, or CMFR. We also call that a CSTR. Okay, So this type of reactor, what this means is that we're having a reactor that has a certain inlet and a certain outlet, right? So we're basically pushing fresh inflows into the reactor. Well, there's a stirrer in the reactor. That's guaranteed that everywhere the concentration is the same, okay? So because of that, at the outlet, the concentration is going to be equal to the concentration within this tank here, okay? So for this system, it's the same with the PFR, which means that there is no accumulation taking place. So whatever the mass is in is going to be equal to the mass out plus the mass reacted, which is quite similar to the PFR again, okay? So now if we calculate the mass in and mass out, let's see what we have. So the mass in is going to be C in multiplied by Q, and the mass out is going to be equal to C tank, or just we can write it as C out multiplied by Q, and plus R multiplied by V, okay? So further, we know that R is equal to Kc, right? C out Q plus Kc multiplied by V. So since this is a well-mixed or completely mixed reactor, so this concentration within this tank is going to be equal to the concentration of the outflow. And this is the reason why we can further calculate what is the outflow concentration directly based on the algebraic relationships. Because further, let's say if we assume that V divided by Q, which is the basically the characteristic time for the flow to mix within this tank here, let's assume that this is equal to theta, okay? So first, let's take out the C out. On the right hand side, you can see that C out multiplied by Q plus KV is going to be equal to C in Q, okay? So the C out is equal to C in divided by 1 plus K theta, okay? So this is what we can obtain from here, okay? So you can see that both for the PFR and the CSTR, they can have inlet. They can have basically have a continuous flow going in and coming out. So this is these reactors are the best suited for the flows that continuously go through this reactor here. So this is not like a batch reactor, although the CSTR or the CMFR looks like a batch reactor, but we basically have a inlet and outlet that continuously let the mass to go through this reactor here. And that is why the reaction rate for this batch reactor and the CSTR are different. So how do we compare the performance of the PFR and the CMFR? So which one is better? Okay, so now let's do a simple comparison here, okay? So let's assume that there's a wastewater treatment process, right? It's treating a total volume of 5,000 meter cube or cubic meter, okay? So the initial concentration, C0, is 100 milligram per liter, and the flow rate is 1 cubic meter per second, okay? So because of that, for a PFR, we know that the time is going to be equal to volume divided by flow rate, right? Which is equal to 5,000 second, okay? And 5,000 second is basically 1.4 hours, okay? And further, we know that the reaction constant for this first order reaction, K, is equal to 2 per hour, okay? So it wants us to calculate what is the removal efficiency. So for a PFR, we know that C0, or the final concentration, is equal to C0 multiplied by the exponential minus KT. Okay, so we know that the initial concentration is 100, and then this is going to be exponential of minus 2 multiplied by 1.4. So you can find out that the final concentration is 6.08, right? And if we want to calculate the removal efficiency, or the this processing efficiency, then that's going to be C initial minus C final divided by C initial. Okay, you can see that for a PFR, the removal efficiency is 94%. And similarly, we can calculate the final concentration of a CSTR or CMFR, right? So if you think back on the equation, we're going to use C out equal to C in divided by 1 plus K theta, right? C in is 100, and here we have 2 multiplied by 1.4. Okay, so the result turned out to be that the C out is 26.3 milligram per liter, and the removal efficiency is 74%. So you can see that the PFR indeed have, by comparing these two reactors, the PFR has a higher removal efficiency, which means that it is more efficient when we are trying to use certain reaction to process these chemicals or to process these pollutants. Okay, so what is the reason there? So what is leading to this result? Okay, so is it because that the PFR mix better? It is not the case, right? The PFR doesn't involve any mixing. Okay, is it because the concentration in the PFR gradually decreases, or is it because the reaction is zero order? And this is of course not, right? Because we're dealing with first order reactions. And it turns out that it is actually because of the second point here, because the PFR or the reaction rate in the PFR gradually decrease. So if you think about the concentration within the PFR as a function of time, okay, so the concentration is going to gradually decrease, which means that the concentration of this species, let's still consider the reaction from A to B, Ca. So at the beginning, the concentration is going to be the initial, it's decided by the initial concentration, whereas giving it a very large or very high reaction rate. While for the CSTR or CMFR, the reaction rate is always decided by the final concentration, which is basically giving it a relatively low concentration for the reaction to take place, right? So this is going to give us a difference in terms of the reaction rates. And this is also the reason why the PFR has a higher reaction rate or have a higher removal efficiency for these pollutants or the chemicals. Okay? And after talking about the mass balance, we can further talk a little bit on the energy balances. So for the energy balances, we have to know that there's a first law of the thermodynamics. So basically the heat that is absorbed by certain control volume, right? So if it absorbs certain heat amount, right, it's going to be the final internal energy minus the initial internal energy plus the work that's done to the outside. Let's say that we have a bunch of air in a balloon here. Okay, so this is a balloon. Okay, so let's say that the final internal energy is twice of the initial internal energy. So what that means is that it has to absorb energy from outside, right? Absorb heat from the outside. And also if the balloon does work to the outside, let's say it expanded to twice of its volume, it also needs to absorb extra energy or extra heat so that it can do work to the outside. Okay? So this is dictated by this first law of thermodynamics. And further, we can call that the U2 minus U1 is also called as the internal energy increase. Okay, so the U is purely determined by the internal or thermal energy. We also have the law of the heat transfer. Okay, so the heat transfer can be calculated by these differential equations. Right, it involves the area of certain substance. Right. So also we need to consider temperature increase. So the higher the temperature difference, or the higher the temperature difference, the better the heat transfer. Okay, and there's also the second law of the thermodynamics. So second law of the thermodynamics involves how chaotic or how random the system is. Okay, so the energy flows from a region of high concentration to one of less concentration, but not the reverse, and that quantity degrades as it's being transformed. So this is related with how random this system is being processed. And this involves the calculation of the entropy, and we know that the entropy of the universe is always increasing because the randomness of the molecules are always increasing. Okay, so finally, let's try to do a quick review here. So we want, basically in this class, we talk about what is a general mass balance equation, right? We have to consider about the inflow, outflow, accumulation, and also the consumption, right? Accumulation is related with, is basically the dm dt or the dc dt term that's in this equation, in that equation there. And also we try to understand how do we determine the performance of the batch, plug flow reactor, and also the completely mixing reactors. And we'll also discuss which type of the reactor is more efficient. And we'll try to understand why that is the case, right? That's because for the PFR, the plug flow reactor, because it's having a relatively higher initial concentration, so the reaction rate at the initial time is going to be much higher compared to the CMFR, or the completely mixed reactor. Okay, so that's all for the contents of this class, and let me know if you have any questions.